All right, so I want to start off this week with an apology, mainly because the information that we're talking about this week is my jam. So I might give you too much outside information and talk too much. I'll really try to stay on target. It's just that life history theory and its effect on the human life course is what I've been studying my entire career. And so over at UNM, there's a course, Anthropology 1170, that is totally focused on behavioral evolution. And we call that course the Human Life Course. We're trying to get it offered at CNM as well. So far, we have not been successful at doing that. Hopefully, sometime in the future, we will have it. So, what are we going to talk about? We're going to talk about these evolutionary legacies and their effects on the individual. And so, we'll address our evolved biology and how contextually, culturally, we are so different in modern society. And so we'll address this question of whether we have a mismatch between our evolved biology and contemporary lifestyles. We'll explore biocultural evolution and the life course, specifically the human life course. We will compare human growth and development today to that of the past. We will discuss the human life cycle using life history theory as an explanation for it, specifically focusing on the life history stages that we have that are functionally different than those that our nearest relatives have. We will examine aging and longevity, specifically looking at explanations for senescence, and we'll ask the question, are we still evolving? So the focus question for this lecture this week is, how does the flexibility of human behavior pose problems for the species? Okay. There is no doubt that we are among the most, if we're not the most behaviorally flexible species on the planet. We're flexible in what we eat. We're flexible in our cultural expression. We are flexible in our mating styles. We are flexible really across any kind of plane of behavior. And our flexibility specifically is what makes us so successful. What do we mean by this? Well, we definitely have evolved human behaviors, right? But part of what specifically has evolved and what has led to us becoming so adapted to so many different environments on the planet is the fact that we can change our behavior. We can modulate our behavior based on environmental input. And so we call that behavioral plasticity. When we talk about traits being plastic, they are able to be changed pretty easily. Okay. So part of what is so remarkable about the human species is that so much of our behavior is plastic. One of the things that people ask is how can behavior have an evolved basis when it's plastic in its expression? And so we talk about something called reaction norms. We talk about the fact that that what evolves is not a single invariant behavior, but rather a suite of behaviors such that in different environments, different behaviors will be expressed. And this really, really, really is like the secret to our success. Uh, there's no doubt about it that our behavior evolved in this context of foraging as hunter-gatherers. Our evolved psychology, our evolved metabolism, our evolved immunity, all of these things are really examined in this lens of having recently lived as hunter-gatherers. But it's also no question in terms of the pace of cultural change that we've seen in the last 10,000 years. Agriculture was independently invented roughly 12,000 years ago, and agriculture jump-started a pace of cultural change. It changed the way we lived, it changed our diet in huge ways. It led to a lot of the other changes in technology, sophisticated art styles, all of this, all of the really depending on the frame of thought you have, what we consider history, right? History wasn't possible without the advent of agriculture. And a lot of people consider history more exciting perhaps than prehistory, because prehistory was relatively, just doesn't have the same kind of pace of development, the same kind of pace of changes that we've seen. So a lot of what we do is still adaptive. Behaviors that evolved in a foraging context absolutely can be adaptive in a modern context, but a lot of what we do is no longer adaptive. And so we have to ask ourselves, does this change in our contemporary lifestyles, or two contemporary lifestyles, really predicts some of these mismatches, really predict some of these behaviors that are no longer adaptive? So let's think of an example. Conspicuous consumption, right? In an evolutionary context, by having conspicuous consumption, and this would even be true among agricultural societies, you are basically advertising your wealth, and advertisements of wealth were adaptive. They got you more mates, they got you more babies. In a modern context, conspicuous consumption is associated with an increase in garbage, an increase in the use of plastics, an increase in the use of energy, associated with all of these factors that contribute to our climate crisis that we're experiencing. So that's just an example of something that, while adaptive in a hunter-gatherer context, is no longer adaptive. And so that's why we have to recognize these changing contexts, right? The lives of our ancestors differed in many ways from people in nations today. First of all, they didn't sit around a lot. Now, that's not to say they didn't have leisure time. Foraging populations, extant foraging populations, actually have more free time than we do. It's just that their production roles involve more physical work. More physical exertion. So they may only work 3 to 7 hours a day. And the average amount of time spent hunting among the Ache for men is about 7 hours a day. The average amount of time that females spend on foraging activities is only about 3 hours a day. So they've got a lot of time for leisure. They lounge around, they joke, they sing, they play, but they're not sitting at desks for 10 hours a day, right? Our lifestyles are fundamentally very, very different, and it's got some behavioral consequences as well as physical consequences, right? We've got increased obesity. You don't really see that same level of obesity among hunter-gatherer populations. So we shouldn't be surprised that when we look at some behaviors, we're going to find this this mismatch and this maladaptive nature in a modern context. All right, so how can we see such a behavioral mismatch? Well, we've got to talk about biocultural evolution. Okay. Biological development occurs from embryo to old age. There are absolutely aspects of our development, our life course, that are biologically mediated. One of those is the age of menopause. Did you know that the strongest predictor of the age at which a woman will experience menopause is the age at which her mother experienced menopause, the age at which her grandmother experienced menopause? Menopause is first and foremost a genetic trait, a biologically mediated trait. By contrast, menarche is not. We're going to talk later in the lecture about something called the secular trend in the age of menarche. Average age of menarche is first menstruation. The average age of menarche among hunter-gatherer groups is about 16. The average age of menarche in the US right now is about 12.3. So we have definitely seen a changing pace of development during childhood and kind of the entry into adolescence. So that's an example of two traits that very, very, very tightly tie to reproductive outcomes and thusly evolutionary advantages, but have very different causality. Cultural factors interact with genetically based characteristics to change the expression of those traits. And so what is it, and we'll talk about this again, right in later in the lecture, but what is it that has changed that promotes earlier ages at menarche? Well, it's nutrition. And because of increased nutrition, increased access to calories, though those calories may not be as quote unquote nutritious, leads to faster growth rates, faster deposition of body fat, so on and so forth during childhood, which corresponds to earlier age at menarche. When we compare our growth and development across generations, we see some similarities. We also see some predictable differences between now and how we used to grow. We grow from the time that we're conceived, right? We recognize that there is a lot of growth that happens in the first 2 trimesters in utero. Um, and that we start growing from the time we're a little embryo implanting in our mother's uterus. Human growth has predictable timing of what we call growth spurts. Typically, humans will grow throughout their late teens or their early 20s, though we've seen a divergence of patterns of growth between males and females, as we've seen earlier ages at menarche in modern populations. And the three growth spurts um, that individuals experience are in utero. For the first 4 years of life, if you have kids, you've seen how quickly they grow during infancy and toddlerhood. And then during adolescence, we are unique among the primates. Not entirely unique. There are some species of old world monkeys and apes that experience an adolescent growth spurt in males. I mean, for example, gorillas, right? Gorilla juvenile males look very similar to juvenile females, but during adolescence, they rapidly gain body size and they get that silverback, hence silverback gorillas. But we don't see, in particular, female adolescent growth spurts in most other species of primates. So we are pretty unique there. And so one of the things that we have to explain if we want to understand kind of the effects of our evolutionary heritage on these modern legacies is the adolescent growth spurt. We define the adolescent growth spurt as pronounced increase in the growth rate that occurs at some point during puberty. We see some really big differences between males and females in kind of the timing of the adolescent growth spurt relative to other pubertal events. Specifically, girls experience their peak growth spurt earlier in the process before they ever hit menarche, whereas boys experience their peak growth spurt relatively late in the process, certainly after spermatogenesis is already well underway. Uh, so this adolescent growth spurt stands in stark contrast to a fairly steady level of growth from about age 4 to about age 12. So children grow certainly between the ages of 4 and 12, but they grow at a fairly consistent rate. And so what's so remarkable about these adolescent growth spurts is the kind of speed with which it occurs. And so Western teenagers typically grow about 4 inches a year, whereas before they were growing maybe an inch per year. This is then followed by a decline in the rate of growth until adult stature is achieved in the late teens. Okay, so what does this look like timing wise for, let's say, American boys and girls? Well, um, we mentioned already some of the differences in patterns of growth between boys and girls. When we look at growth curves for healthy American girls, and we look at the height in inches based on the year in which they're growing, right, you see a strong slope, a steep slope to the line between birth and age 4, where they grow from about 20 inches to about 40 inches. They double their birth size, right, in terms of their height. Um, then we see it steady, we see it kind of level off and happen at a more steady rate than the rest of their childhood. When we look at the height velocity, the number of inches that they grow per year, this is where we can see those really interesting spikes. So we've got really, really high velocity of growth again for those first 4 years of life, as evidenced by a steep slope. And then we see almost a flat line until about the age of 13 to 14, where we've got this peak in height velocity. So what that means is that girls grow at a steady rate between roughly the age of 4 and puberty, and that early on in this process of puberty, girls experience a growth spurt. They experience an increase in their height velocity. We could plot body weight as well, and we would find steep increases in body weight too. And you think about, for those of you who are biologically female, think about your patterns of growth. Think about your body shape when you were a child versus your body shape when you hit your teen years. One of the things that girls either hate or celebrate is growing things like breasts, but that's not the only areas of our bodies that deposit body fat during puberty. Critically, girls go from having very kind of straight builds where their waist and their hips are about the same circumference to developing curves where suddenly their waist is thinner than their hips and they've got this kind of hourglass body shape to them. We also, not only are we growing our bodies during childhood and even adolescence, but we're growing our brains too. And so we've got these interesting patterns of body size growth, but we've got like different timetables for brain development. So one thing to note is that we are born with brains that are a relatively small proportional amount to our adult brain capacity. And so our brains are only about 25% of their adult brain size at birth. We'll talk about why this is in just a minute. Chimpanzees are born with brains that are 50% of their adult size at birth. Rhesus macaques are born with brains that are 70% of their adult brain size at birth. Some species, like rabbits, are born with like fully adult brains at the time of birth, to where most of their growth is just in body size, not in brain size. At 6 months, our brain has already grown to about 50% of its adult size. It'll reach 75% of its adult size. We've got a typo there. It'll reach 75% of its adult size at 2.5 years. It will reach 90% of its adult size at about 5 years. So please note that mistake. I'll go back and change it, but I'm not going to re-record. So just make that note to yourself that 90% should be at 5 years, not at 2 years. And then it reaches 95% of its adult size by the age of 10 years. So most of our brain growth happens prior to puberty, right? The other really important thing to know about brain growth is that it happens on a predetermined timetable. So you can't really delay brain growth. You either successfully grow your brain during this critical period of development or you don't. And if you don't, you're left with a not fully elaborated, fully adult sized brain, which is going to affect your cognitive function. So this is one reason why infants might be diagnosed with what's called failure to thrive. So infants have evolved to protect brain growth at the expense of growth in other bodily systems. And so failure to thrive is diagnosed when an infant fails to meet kind of growth according to standard growth charts that pediatricians use to make those comparisons. So if babies don't even fall on what's called the growth the growth curve, pediatricians' offices have routine height and weight curves that they'll plot your children on as they go in for their well child checkups. And they'll put them in what are called percentiles. So two of my kids, my two older ones, were always in the 95th percentile or above. That meant they were large birth weight babies. And they maintained that same kind of relationship as they grew. Correspondingly, my son now, at the age of 15, is already 6'4". So, it makes sense. He's always been a big kid. My youngest, though, was born only, well, he was actually born really high on the growth curve, but during his early years was only on like the 25th percentile. Finally, at about the age of 4, he reached the 50th percentile. Now, at the age of 6, he's at the 75th percentile. So he's been doing some catch-up growth. That failure to thrive is when babies don't even fall on the growth curve. And really, what's going on is that all of the calories that they're able to metabolize are going to brain growth so that their body growth shuts down. This can happen for a variety of reasons. One of those, of course, is neglect, right? You don't feed your babies, or you feed your babies on a strict timetable instead of feeding them on demand. All babies should be fed on demand. I don't buy into some of the often religious-based uh, theories that you've got to train your babies upright for predictable sleeping patterns and eating patterns. That's not true. Babies grow at their own pace. You need to provide food on demand. When they're hungry, you need to feed them. When they're tired, you need to let them sleep, within reason, right? Um, but so keeping a strict schedule, or kind of monitoring exactly how many ounces they get and not letting them feed until they're done feeding, those can certainly be reasons for failure to thrive. But failure to thrive can also be an indicator of like metabolic disorders. We've got about 60 metabolic disorders, genetically based metabolic disorders, that are tested for in New Mexico in that 2 week the blood test at 2 weeks, when you kind of follow up with your pediatrician. And so they will do the heel prick, and they'll put it on a card. They'll send it off to the health department. The health department will test for various metabolic disorders. Some of those metabolic disorders have to do with not being able to metabolize a particular amino acid, and treatment is as simple as just minimizing the intake of that amino acid. And so by avoiding diets that contain that amino acid, then babies are able to grow normally. So just to note that babies will shut down all of their body growth in order to preserve that brain growth, because if that brain growth doesn't happen on this predictable timetable that's predetermined genetically, that brain growth will not happen. So don't starve your babies, right? Let your babies eat when they're hungry, sleep when they're tired. Anyway, so such a small amount of growth before birth is really unusual across mammals, not just primates, but really across all mammals. So we have to ask ourselves, why? Why do we give birth to such small-brained infants? Because it's really a question of interest, right? I mean, it's great that our babies grow their brains after birth, but why do we give birth to such helpless infants? The other mammals that give birth to really, really helpless infants are marsupials. Have you seen, and panda bears to some degree as well, have you seen the size of a kangaroo joey when it's first born? They're like less than 3 inches. And kangaroos can get fairly large body size. So marsupials specifically adapted that way to um, basically cut their losses, per se, so that if conditions weren't suitable for continued gestation inside the pouch, they could really, really quickly just kind of dump that pregnancy and later on try again. Placental mammals committed themselves to this longer period of gestation where you couldn't really cut your losses as easily. And I mean, placental mammals dominate most of the world, right? Marsupials are only in Australia, and then opossums being in the New World and other places. So obviously, what placental mammals did conferred a larger advantage than what marsupial mammals were doing. But comparatively, our babies are born pretty helpless. So the main, or I guess most mainstream theory for the underdeveloped uh, size of our brains when we're born is what's called the obstetrical dilemma. And what this proposes is that the size of our birth canal is really mediated through the constraints of bipedality. So we have talked week after week about kind of the importance of bipedality, how it was energetically more efficient. The obstetrical dilemma assumes that we are constrained in the size of our hips by the energetics of movements, that bipedality makes us basically have narrower hips. And so, according to the obstetrical dilemma, the reason that we give birth to small, proportionately small brained infants is because any bigger and our babies would get stuck in the birth canal. And absolutely, like, there's some evidence that corroborates this. Babies with bigger head sizes can get stuck in the birth canal. Babies with bigger birth weights can get stuck in the birth canal. Our heads, and I'll show you a slide on this a little bit in a few, our heads are proportionately, like, basically the maximum size that can possibly fit through our birth canal. However, there are some criticisms of this, and um, we'll talk about some of that. So, one of the competing theories as to why babies are born at the size that they're born has more to do with the energetics of gestation and growth. Basically, maternal metabolism, there's a cap on the rate at which um, mothers can turn the calories they consume into nutrients that pass through the placenta. And that babies are born not when their heads reach some critical size beyond which they can't fit through the birth canal, but rather when that ability of the placenta to translate calories the mother eats into nutrients passed to the baby maxes out. And that the energetics of pregnancy, it's really phenomenal. Kind of the metabolic stress that females are put under while they're pregnant. And we can see comparatively among other primates that it really has, because their heads never reach a size where they're too big. I mean, eventually, but not usually, reach a size where they're too big to fit through the birth canal. This obstetrical dilemma doesn't take place in other primates. Rather, other primates are born at a point where mother's metabolism can no longer convert calories into enough nutrients, and so she has to switch to providing breast milk so that growth rates can be sustained at those higher rates. We're just like other primates with respect to that. So we grow absolutely as fast as we can and as much as we can in utero, but there's this point where further intrauterine growth can't happen because our metabolism can't keep up with that, and our placenta can't convert what we eat into nutrients passed on to the offspring. So the obstetrical dilemma, regardless what textbooks say about it, um, it's slowly being disproven by some of the more interesting research that's being done with respect to gestation and um, lactation and birth. One other thing that's really significant, though, not as a predictor, I mean, our focus on cultural learning doesn't predict that our brain should be small at birth. It's not the evolutionary cause for it, but it is an added benefit once we already committed to that pathway. And so the fact that so much of our brain development takes place in like after we're born and in this specific cultural context, that is really, really significant. Okay. So while it's not an explanation for the evolution of giving birth to small brain babies, once we, through the constraints of energetics, started giving birth to small brain babies relative to adult brain size, it opened up this entire avenue for rich cultural brain development, towards brain development that could be amazingly plastic, that could allow us to make different decisions in different ecological contexts, that could produce thousands of different languages, that could change emotions based on cultural context. I mean, all of this really significant stuff. Okay, so why do we give birth to small brain infants? Well, it's a constraint of the energetics of gestation and growth. And, that then relates a little bit to this obstetrical dilemma. If we had to give birth, though, to larger brain infants, we could make our hips wider and it wouldn't be that big of a deal. It wouldn't interfere with the energetics of and kind of the function of bipedality. Once we give birth to small brain infants, there's absolutely this huge evolutionary benefit in the cultural learning that takes place among those infants. So most of our neurological growth occurs under the influence of culture. So there's no way that we can separate out biology and culture when we're looking at human behavior. All right, so what are the nutritional requirements for growth? Well, the nutritions needed for growth, development, and body maintenance include proteins, carbohydrates, fats, vitamins, and minerals, right? Our macronutrients, our micronutrients. The amount that we need of these nutrients co-evolved with the foods that were available to humans throughout our evolutionary history. And so we're going to look a little bit at the dietary makeup that foragers live with versus what we see in a modern context. Deficiencies that mothers experience during pregnancy can last throughout the new child's lifetime and even beyond. So more and more research is pointing to the role of the intrauterine environment as an epigenetic factor. This is part of what's behind the discussions of inherited trauma and such. Your adult metabolism. Okay, so if I were just to ask you the question, what makes people fat? What would your answer be? Most of you would probably think or say some variation of people get fat when they consume more calories than they expend. Now, that being said, right, we have an epidemic of obesity in places like the United States. If we know why obesity happens, i.e., you eat more calories than you expend, then we should also know how to fix it, right? Well, I just want you to reflect on your own personal characteristics, the people that you know, your family members, yourself, etc. I will be the first to admit that I am fat. Okay, a lot of people, and it's really bad in the medical community, right? I go in because I have joint pain or pain in my foot. I'll give that example. I had pain in my foot that I walked around on for 5 months, and it was chalked up to me being fat. And if I just dieted and exercised more, then magically the pain in my foot would go away. Well, I spent 5 months walking on a stress fracture. Like they wouldn't even X-ray until like 5 months later, my foot was still bothering me. It took a second opinion, a different orthopedic practice, just to even get an X-ray to rule out the stress fracture, right? So, you ask that question of why are people fat, and sure, some of it is you eat too much. You watch shows like My 1,000 Pound Life or whatever on TLC. Those are going to be cases of if you're eating a loaf of bread a day, you're probably eating too much, right? But it's not that easy. As someone who's been overweight my whole life, I have had times where I've dropped a lot of weight. Where I was the equivalent of like a size 6 in US sizes. But in order to maintain that, I had to spend a minimum of about 3 hours doing cardio every single day. So this was a time in my life before I had kids where I would go for like, oh, I think I'll do a 10-mile trail run today just for fun, right? Which is all well and good, but when you work full time, when you have kids, you've got to make different decisions, right? And I don't have a spare 3 hours a day to exercise. I exercise 3 to 4 times a week at CrossFit and have some phenomenal strength and stuff. I eat a healthy diet. I eat according to like the whole life challenge kind of stuff, minimizing grains, focusing on lots and lots of fruits and vegetables, etc., healthy fats, not a lot of like saturated, red meat fats. I don't do keto with bacon, for example. And still, I'm fat. So, it's not that simple. There is a genetic basis to fat. to obesity, to holding on to weight, but it's not even simply that. It's not a matter of really the genes that you have. It's a matter of these epigenetic factors. And so, if your grandmother experienced food stress when she was pregnant with your mother, that meant she experienced food stress when the eggs that your mother developed that eventually led to you and your siblings were laid down. Because we are, as women, we are born with all the eggs we will ever possess. And so it is your grandmother's intrauterine environment, those eggs that are being laid down in your mother's reproductive tract while she's gestating in your grandmother's uterus. Those are carrying marks of your grandmother's nutritional stress. My grandmother grew up during the Great Depression. Um, so when my grandmother was uh, pregnant with my mother, she was still experiencing, they were really poor. She was still experiencing a time of food stress. So when the eggs that were responsible for me were laid down in my mother's ovaries, they developed with kind of that program to be a calorie hoarder. So regardless of what I eat, whether I eat 900 calories or I eat 3,000 calories, I stay heavy. You know, I could starve myself and be like below 500 calories and eventually probably lose some weight, but that's not going to be in a way that's realistic, right? So, this is just to bring up the fact that, you know, when we talk about this environmental component, sometimes that environmental component seems distanced from um, like the actual like trigger, right? Like your development in utero happened maybe 20, 30 some odd years after your grandmother gave birth to your mother. um, but we still have that kind of inherited epigenetic effect. So we talk about inherited trauma. The grandchildren of Holocaust survivors have markers in their DNA for the same reason. The grandchildren, great grandchildren of former slaves have markers in their DNA for the same reason. So, if we want to, for example, predict why people of color are obese versus white people being obese, we have to look at something more complex than people of color eat crap, right? They eat the standard American diet, they eat chips and drink soda, etc. That is a function of poverty in food deserts. That is a function of having kind of like minimal healthy foods available. If you look at the government aid that's come to Native American reservations, for example, it's government cheese and peanut butter, basically, right? But that's also an effect of our historic kind of colonialism and mistreatment of people of color. So, yeah, there's my soapbox. There we go. All right. So, deficiencies during pregnancy can have really long lasting effects. The specific pattern of amino acids required in human nutrition, what we define as the essential amino acids, or those that have to come from food, reflects an ancestral diet that's high in animal protein. Okay. So, from an evolutionary basis, we're not vegetarian. Now, does that mean you can't be healthy and be vegetarian in a modern context? No, absolutely not. It doesn't mean that. At the time that I was at my thinnest, I was vegan. I was vegan for about 7 years. Critically, I probably didn't consume enough protein, but that's in retrospect. And when I got pregnant, I couldn't stay vegan because morning sickness made it to where I couldn't stomach my protein sources that I was utilizing. So we've got an evolutionary history of diets high in animal protein. There are 9 amino acids that have to come from the food we eat because our body doesn't synthesize them. Those include histidine, isoleucine, leucine, lysine, methionine, phenylalanine. That phenylalanine is one of those that's a metabolic disorder. It's phenylketonuria, that where babies can't digest phenylalanine, and so that PKU test is one of those metabolic tests. Threonine, tryptophan, and valine. Those are our essential amino acids. If you do not consume those in your diet, then you have to take amino acid supplements. You've got to supplement your basically your micronutrients. So when we compare diets from a pre-agricultural diet to contemporary diets and what's currently recommended, the US RDA, right? Pre-agriculture diets were 33% protein. Contemporary diets are only 12% protein, and our protein that's recommended by the US RDA is 12%. Pre-agricultural diets were 36 or 46% carbohydrate. Modern diets are 46% carbohydrate. What's recommended relatively recently is 58%. So interestingly there, the carbohydrates that we consume in contemporary times and in this kind of agricultural context are cereal grains. They're simple carbohydrates. The carbohydrates that we consumed evolutionarily are complex carbohydrates, mostly like fruits and vegetables and tubers. So optimal diets would not be high in cereal grains, though we have had in some areas of the world about 30,000 years of cereal grain consumption. So the rice consumption that we see, for example, in East Asia doesn't seem to be a problem because we have been doing that for 30 to 40,000 years. That's not carbohydrates that are making people fat. The corn consumption in the New World is. We've only been consuming that for about 4,000 to 5,000 years. All right, so our pre-agricultural composition of fat was 21%. In contemporary diets, it's 42%. It's a recommended 30%. The kinds of fats that we were eating are very, very different. We should be focusing on a diet high in omega-3s. What we end up with, though, is a diet high in omega-6s that has negative health consequences. So if you're really, really like attuned to and want to know what the best sources of fats are, stay away from vegetable sources of fats. Coconut oil, not much of a problem. That's okay. Fatty fish oil, absolutely essential. Omega-3s also come from things like walnuts, to some degree almonds, though almonds are not really eco-sensitive because they take so much water to produce one crop of almonds, so on and so forth. But stay away from corn oil, canola oil, things like that. Those are high in omega-6s, not high in omega-3s. Alcohol consumption. We didn't really have much of it when we were pre-agricultural, but we sure enjoyed it once we started producing grains because grains can be fermented. That's not to say that indigenous populations didn't ever consume alcohol. They would eat fermented fruits and they'd feel relaxed when they did so. But it wasn't as pervasive as it becomes once we develop agriculture. Agricultural contemporary diets, 7 to 10% alcohol among adults. We might view that as problematic, thinking about brain development and functioning. Cholesterol, pre-agriculturally, we would have had about 520 milligrams of cholesterol. Contemporary diets have between 300 and 500. It's recommended about 300. Your cholesterol actually is much more heavily predicted by your genetics, your family heritage, than it is your consumption. Eating the yolks of eggs does not really give you high cholesterol. When we look at fiber, pre-agriculturally, 100 to 150 grams of fiber. Contemporary diet, 19.7. It's no surprise that we have problems with our poop, okay? Yeah, there it is, very blunt. We have major poop issues. And we have an entire industry that's focused to helping you poop, right? Laxatives, fiber supplementation, Metamucil, things like that. There's a heck of a lot of stuff that you can take to help you with poop. Pooping wouldn't have been a problem in our pre-agricultural diet. So changing the form of the carbohydrates that we ate has changed our poop. Tubers were good for us, roots and tubers. So that's talking about things like potatoes. Well, so you might think, therefore, French fries are healthy. Well, you don't eat the peel when you're eating the French fries. We would have gotten a lot of fiber and vitamins from the peel of the tubers that we would eat. So it's not that potatoes are unhealthy. It's more that we process them in different ways. When I make mashed potatoes, I always make them with the peel still on because a lot of the good stuff is in the peel. Sodium, 690 milligrams pre-agriculturally, 2,300 to 6,900 in a contemporary diet with a recommendation of 1,000 to 3,000. So we are definitely consuming a lot more sodium. Calcium, 1,500 to 2,000 milligrams. Contemporary diets with 740, recommended between 800 and 1,500 milligrams. We all probably need more calcium. The way to get that is not necessarily through milk unless you're using full fat dairy products. Skim dairy products don't help you. We would have gotten a lot of calcium through leafy greens when we were living in pre-agricultural context. And then ascorbic acid, 440 milligrams in pre-agricultural diets, 90 milligrams in contemporary diets. We're only recommended 60 milligrams. Huge, huge changes with the advent of agriculture.